Alright, today we are going to consider Bremsstrahlung, Cyclotron and Synchrotron radiation to finish the topic of radiation and the corresponding chapter. So, we will discuss first the relativistic Larmor formula. Previously, we considered this in the case when the particles move non-relativistically. Okay, so now I would like to extend this equation to the general case for the when we have radiation from a single source, from a single charge. So, and previously we considered only the radiative part of the electric and magnetic fields. Today we will do the same, so we will consider only the radiative part, which behaves as and drops off as 1 over r, right? So you remember probably that in electric and magnetic field, so let me remind you, in electric and magnetic field we had two contributions over here. One of them fell as r squared and another fell as r. So this is the piece which we are interested in, and this is the piece which we are going to work with. All right, when we're computing, of course, Larmor formula. So we will start with the pointing vector first. For the pointing vector, we will have, from the definition of the pointing vector, we have 1 over 0 multiplying E cross B. In electric and magnetic fields, we already computed, so we will only keep 1 over r pieces for both of them to get the following expression. So for now, we'll just use the information for the dependence of the magnetic field. All right, so how the magnetic field looks like. So this is the last equation that we discussed over here. For the single particle source, for the single charge source, and it's given by this expression, 1 over c r cross E. And simplifying this, we'll obtain this is 1 over times the unit vector in the r direction. So as a reminder, so all of the quantities on the right hand side here are computed at the retarded time. So everything here is computed at retarded time. Yeah, so what it is, I will remind you again a little bit in the below, but just let's scroll it back. So the retarded time is t prime, which satisfies this equation, right? So, but again, so I will remind you about this again, as the time comes. All right, so taking the value of the term which drops as 1 over r, substituting to this equation, we'll obtain the following expression for s. S equals q squared divided by 16 pi squared epsilon 0 c to the power cubic. Now you will have the absolute value of pretty complex expression. It's r crossed with the vector r minus bc vector, and that in its turn is crossed with acceleration vector a. So the bracket closes, and then we square this. We divide this by the factors of kappa. I will remind you what kappas are in a second. Kappa to the 6, r squared, and everything is multiplying the unit vector r, right? So the multiplication of the unit vector r came from this piece, right? So okay, very good. So what kappas are? Kappas we introduced last time. Simplifier expressions. They are given by 1 minus r hat times v divided by c. Again, so everything is computed at the retarded time t prime, and this T prime is defined by the solution of this equation, okay, where capital R we defined previously. Okay, so now this means that the coordinates that I set up, we can set up the coordinate in such a way as we can integrate S, right? We can integrate S, the pointing vector, over a sphere of radius R, over a sphere with radius R that surrounds particle at its retarded time, right? We will consider radius, a sphere with a radius R which surrounds particle at its retarded time. Okay. There is, when we will do that, there is a subtlety which is associated to the Doppler effect. Okay, so the subtlety is the energy emitted per unit time. Energy per unit time t is not the same as energy emitted per unit retarded time t. Not the same. Okay, they differ by the factor, and this factor is just given by this derivative prime. If you remember, this derivative we defined this factor kappa, so they are different by this kappa. So therefore, the power emitted apologies, it's single m double t, emitted per unit time t prime and per solid angle omega is given by okay. Then we will have the factor kappa again, so that's comes from this prefactor. We'll have the radius of this field, it's r squared, and then we have when we do this integration, we will have the vector s, the pointing vector, okay, times the unit vector in the direction of in the direction orthogonal to our sphere, right? So normal to our sphere, and will be just r hat, right? Okay, so then we can substitute everything into our expression and to get this is essentially the same expression. There will be less powers of kappa in the denominator, right? And a couple of r hats will go away. So this is what we are going to get, minus v divided by c cross a, brackets close, and everything squared here. So let me clean this up a little bit. Okay, so we got this vector, and what we are doing here, we are finding its magnitude squared. Okay, and it is divided by kappa now to the 5th power, because one of the kappas cancelled out. Now to compute the emitted power, we must integrate this expression over the sphere, right? over these angles. This is somewhat tedious. I will only provide you with the result, and the result is given by the following. So the total emitted power is given by q squared divided by 6 pi epsilon 0 c cubic. Now there will be quite a large power or gamma to the force. There will be contribution from the acceleration plus another term which contributes as gamma squared divided by c squared times v dotted with a. The velocity times acceleration squared. Okay, this will obtain this expression, and this is a relativistic version of the Larmor formula. Okay, we're going to use both expressions for the distribution of the power of the solid angle and for the total power in a little bit for different setups. So let's consider the first one. Let's consider what is called Bremsstrahlung. Bremsstrahlung. Okay, Bremsstrahlung is from the German word, which is just breaking radiation. So the Bremsstrahlung occurs in the situation when the particle deaccelerates. So in this case, we will consider V to be parallel with the acceleration. Okay, and the particle just moves along some, let's say, line, and it just deaccelerates. Okay, maybe eventually it just stops. Okay. So we'll consider some point x. So let's consider some point x at which the radiation reaches us from the retarded point of the particle trajectory. Right, so we had a particle located at R, and radiation reaches us at the point X. Right, so as before we defined as a difference of these two vectors. Okay, and let's introduce the angle. So the particle moves along some trajectory, right? So let's define the angle between the trajectory and this vector, capital vector R. So we will define R hat times V to be given by the absolute value of the velocity times cosine of the angle between them, cosine theta. Okay, since the term V cross A vanishes in this situation, we are considering V to be parallel with A, the angular dependence of the radiation becomes pretty simple. Okay, we can just write it down. We're using this fact in this expression over here. We will obtain density the omega is given by q squared acceleration squared divided by 16 pi squared epsilon 0. There is c cubic, and finally there is angular dependence, which is sine squared theta divided by 1 minus v over c times cosine theta, and that is to the 5th power. Now that came from kappa. Okay, so if we consider, so let's just analyze this equation a little bit for the angular dependence of the Bremsstrahlung radiation. Okay, so in this expression, if we consider V to be much smaller than C, then the denominator of this expression of this angular dependence will significantly simplify, and we will just get sine squared theta angular dependence, right? And in this case, the radiation will be peaked when this sine square is maximal. That means that the angle theta will be pi over 2. That is, the radiation is mostly going in the direction perpendicular to the trajectory of the particle. Okay. Now, if we consider the situation when V approaches C, the situation changes because the denominator here becomes very small when theta approaches 0. As a matter of fact, we can find the maximum value of the angle at which this expression is maximal. Okay, we just maximize it. We maximize theta as a function of V. So we maximize this part. Okay, and considering the limit when V goes to C, we will obtain the following expression for the angle theta. It will be plus minus square root of 1 minus V over C divided by 2. Okay, this expression. So you can see that when V approaches C, then most of the radiation goes in the forward direction of along the trajectory. So forward radiation along the trajectory. So when V is not exactly C, right? For the charge, most likely the case because the charges are massive, right? And they will never approach C exactly. So when V approaches C, we would see, so this is the trajectory of the particle, and the radiation will be in 2 lobes over here, defined in the forward direction, and the maximum angle for this radiation over here, right, will be given by the angle theta max. Let's write theta max. All right, so now the total power emitted in this case, okay, so we get the equation for the emitted power, we substitute the facts about acceleration and the velocity, that they're perpendicular to each other, we'll obtain the expression that P in this case, or parallel to each other, we'll obtain that the total power radiated is given by Q squared gamma to the 6 times a squared, the acceleration of this particle, of this charge, divided by 6 pi epsilon 0 c cubic. Okay, that's the total power radiated for the Bremsstrahlung case. So now we are going to consider cyclotron and synchrotron radiations. Okay, suppose that the particle travels in a circle. Right, so a particle travels in a circle. In this case, we also know something about the particle velocity and its relation to the acceleration. V dot A in this case is 0, right? The acceleration is perpendicular to the velocity. Again, we are considering the case when a particle is traveling in a circle. So let's consider the axis such that A will be aligned. Okay, A will be aligned with the x-axis instantaneously at that moment of time, and V is aligned with z-axis. Then we can parameterize our unit vector r using these angles, you'll get sine of theta, cosine of phi, x hat plus, and it's essentially just spherical coordinates, sine of theta with unit radius, of course, times sine phi, y hat plus cosine theta z. Okay, we will use this parameterization for r, assuming this alignment of the axis. Then we will do again a little algebra. We will take this vector, substitute into this equation over here, and simplify it as much as possible. Okay, so it's a little bit tedious, but I encourage you to check that. We'll get cubic 1 over 1 minus v over c times cosine theta to the cubic power times a bracket square phi c cosine theta squared. Okay, and the relativistic limit the angular dependence simplifies a lot, and we'll just give the prefactor which will look like as 1 minus, it's just simple. This will drop out, this will drop out, gamma will become 1. You'll get 1 minus sine squared theta times cosine squared phi. Alright, in this limit, the radiation is referred to as cyclotron radiation. Okay, in this limit, this radiation is referred to usually as cyclotron. So now, let's consider the ultra-relativistic limit is approaching C. The radiation will be again beamed mostly in the forward direction. You can compute the angle dependence. I'm not going to do it here, but one again can evaluate the maximum angles using this expression. I'm not going to do that here. So, and again, so the radiation obviously will change its angular profile quite significantly because when this factor V over C is close to 1, then this denominator will become very small, and 1 over the denominator will give you a large contribution. Okay, so you can also see by doing this calculation that will happen when cosine of theta is close to 1 or theta is close to 0, and that would define you the forward direction of the particle, as z-axis is aligned in this case with the v-axis. Okay, again, so beamed mostly in the forward direction, and the total power which will be emitted that way. So this, in this case, this radiation is referred to as cyclotron radiation. Cyclotron radiation, and the total power emitted in this case is given by q squared gamma to the force a squared divided by 6 matter of fact, if you compare, this is synchrotron radiation. So if you compare this expression that we got previously for the Bremsstrahlung and for the synchrotron radiation, they're almost the same, but note that the number of gamma factors is different compared to Bremsstrahlung. Okay, so you can compare these two expressions, and they're different by a gamma square. All right, so with this, we are closing this topic for now, and we'll move on to electromagnetic field in the medium.